It is negative 40 degrees outside, the kind of cold that freezes your eyelashes in 30 seconds flat. The kind of cold that kills engines, cracks pipes, and sends grown men running for the nearest building. And yet, right here, in the middle of the Alaskan wilderness, there's a man standing outside a metal hut, wearing a smile because inside that hut, it is 70 degrees, not 60, not 55 with 3 blankets and a prayer. 70 degrees. Shirt sleeve weather. The same temperature as a comfortable apartment in Miami. That is a 110-degree difference. Sustained day after day to the most brutal winter on the North American continent. And the crazy part? He is not using some massive industrial heating system. He is not spending a fortune on fuel. He is not hooked up to any grid. He built this himself, with his hands, in Alaska. And today, you're going to learn exactly how he did it. Because if you understand what he built and why it works, you will never think about cold climate construction the same way again. This is not a survival gimmick. This is not a trend. This is real Alaskan engineering, battle-tested over decades, and it is available to any man willing to learn it. Let us start at the beginning. Most people who try to build in Alaska fail for the same reason. They bring their lower 48 thinking with them. They build a box, slap some fiberglass insulation between the studs, and wonder why their heating bill is destroying them by November. Alaska does not care about your building codes from Ohio. Alaska does not care about your weekend cabin experience in Montana. Alaska is a completely different animal, and it demands a completely different approach. The man you see in this image understood that. And instead of fighting the climate with brute force, bigger heaters, more fuel, thicker walls, he did something smarter. He changed the shape of the building itself. That structure behind him is called a Quonset hut. And before you dismiss it as some kind of military surplus shed, you need to understand what that arch actually does, because it is one of the most clever structural decisions a man can make when he is building in extreme cold. The Quonset hut was originally designed in 1941 for the United States military. They needed structures that could be shipped anywhere in the world, assembled by soldiers with zero construction experience, and survive conditions that would destroy conventional buildings. They needed something that worked, and that arch was the answer. Here is why the arch matters in Alaska specifically. Snow is heavy, dangerously heavy. Wet Alaskan snow can weigh 60 pounds per cubic foot. A flat roof accumulates that weight directly. A pitched roof sheds some of it. But a curved arch? The snow slides off continuously. There is no flat surface for it to collect on, no corners where ice builds up and concentrates stress, no edges where freeze-thaw cycles crack and compromise the structure. The arch distributes every load, wind, snow, ice, around the curve and into the ground. It is the same principle that makes an egg nearly impossible to crush when you squeeze it from the ends. You are not fighting the weather. The shape is fighting it for you. That alone makes it worth considering. But there is more. A Quonset hut kit can be ordered and delivered to almost anywhere in Alaska. It arrives as flat panels of corrugated steel. No massive timber framing required. No crane. No specialized crew. 2 or 3 men with basic tools can assemble the shell in a matter of days. In a state where lumber costs are brutal and skilled labor is even more expensive, that matters enormously. You are getting a structurally superior building at a fraction of the cost and logistical headache of conventional construction. But here is the thing, and this is critical. The metal shell by itself is not the solution. It is just the beginning. Raw corrugated steel conducts cold like a wire conducts electricity. If you crawled inside an uninsulated Quonset hut at negative 40, you would be dead before morning. The metal would pull every joule of heat out of your body and transfer it straight to the outside air. The shell is not what keeps this man warm. What happens after the shell goes up, that is the secret. When the shell is standing, the real work begins. The interior surface of every single metal panel gets covered in closed-cell spray polyurethane foam. Not open cell foam, not fiberglass bad stuff between ribs, not rigid foam board taped to the walls. Closed-cell spray foam, applied in continuous layers directly onto the metal. This is the single most important decision in the entire build. Here's what closed-cell spray foam actually does, and why it is so different from what most people think of as insulation. First, it creates a completely seamless thermal barrier. There are no gaps, no seams, no edges where cold air can sneak through. When you spray foam over corrugated metal, it fills every ridge, every valley, every bolt hole, every penetration. The result is a continuous skin of insulation that has zero air gaps, and in extreme cold, air gaps are where your heat goes to die. Second, closed cell foam has one of the highest R values per inch of any insulation material available. R value measures how well a material resists heat flow. The higher the number, the better it insulates. Fiberglass bat insulation, the pink stuff you see in most American homes, delivers roughly R 3.5 per inch. Closed cell spray foam delivers R 6 to R 7 per inch. In Alaska, building codes for extreme cold zones typically require a minimum of R 38 to R 49 in walls and ceilings. At 6 inches of closed cell foam, you are hitting R 36 to R 42, right in that target zone, from a single material applied in a single process with no assembly and no gaps. Third, and this is the part people rarely talk about, closed cell foam adds structural rigidity to the shell. When you coat the interior of a curved metal structure with several inches of dense foam, you are essentially bonding the panels together from the inside. The building becomes stiffer, more resistant to racking from wind loads, more durable across freeze-thaw cycles. You are not just insulating, you are reinforcing. And fourth, this is huge in Alaska, closed cell foam is an excellent vapor barrier. It does not absorb moisture. In extreme cold climates, moisture infiltration is one of the leading causes of structural failure. Warm, humid interior air pushes outward through walls. When it hits a cold surface inside the wall assembly, it condenses. That liquid water then freezes, thaws, and over years it destroys insulation, rots wood, and compromises the entire envelope. Closed cell foam stops that process cold. The foam itself is the vapor barrier. There is nothing for moisture to travel through. The wall stays dry, the insulation stays effective, and the building stays intact for decades. This is why Alaskans who know what they're doing choose the system. It is not the cheapest option up front. A professional spray foam crew with proper equipment and respiratory protection will cost more than rolling out fiberglass bats. But over the lifetime of the building in this climate, it is not even a competition. Now, the foam handles the walls and ceiling, but there's a third surface that beginners always underestimate. The floor. The ground under a building in Alaska is not neutral. It is actively trying to steal your heat. In many parts of Alaska, the ground is permafrost, soil that has been frozen for hundreds or even thousands of years. In other areas, it freezes deeply every winter and thaws every spring. Either way, the ground is cold, profoundly cold. And if your floor is in direct contact with that ground, or even connected to it through an uninsulated slab, you are losing heat constantly through the bottom of your building. This is a step that wrecks builds that should have worked. A man can do everything right. Perfect foam coverage on walls, a great heater, good door seals, and still have a cold building because he ignored what is happening underneath him. There are several approaches that work. The first is an insulated concrete slab. You pour rigid foam board, typically 2 to 4 inches of extruded polystyrene, which holds R value even when compressed, directly under the concrete before the pour. The foam sits between the cold ground and your living space. The slab holds heat rather than conducting it away. The second approach is elevated wood framing. You set your Quonset hut on pressure-treated posts or a perimeter foundation, build a wood floor deck above the ground, and insulate the cavity between the deck and the earth with rigid foam or even more spray foam. The air gap on the floor, provided it is properly managed, adds another buffer zone between you and the frozen ground. The third option, common in very remote builds where concrete is impractical, is a thick, rigid foam board laid over compacted gravel, topped with plywood subflooring. It is the lowest cost version, and it works remarkably well for a seasonal or remote use structure. Whichever method you choose, the principle is the same. Your floor must be thermally separated from ground. Treat it as seriously as you treat the walls. Now the structure is standing. The foam is on the walls, the ceiling, the floor is insulated, what heats the space. Look at the image again. That plume of smoke rising from the roof vent tells you everything. There's a wood stove or a propane combustion heater inside, almost certainly a small one, and that is not an accident. That is intentional. Here's a counterintuitive truth that most people get wrong when they build in cold climates. They think bigger heat equals warmer building, so they install oversized heaters because they are scared of being cold. But in a properly insulated structure, an oversized heater is a problem, not a solution. A well-insulated building holds heat. It does not bleed it. Once the interior mass, the air, the furniture, the foam itself, absorbs heat up to your target temperature, you only need to replace the heat that leaks out. And in a well-built Quonset hut with proper foam coverage, that leakage rate is surprisingly low. A small, efficient wood stove running on locally harvested timber or a modest propane heater can maintain 70 degrees in this structure even when it is -40 outside. The heater does not have to work hard because the building is doing the work of holding heat. This dramatically cuts fuel consumption, which in remote Alaska, where propane deliveries are expensive and firewood takes time to harvest and process, is the difference between a sustainable homestead and a money pit. There is one critical safety consideration that cannot be glossed over here. A sealed, well-insulated structure needs combustion air for the stove and fresh air for the occupants. Carbon monoxide is invisible, odorless, and lethal. Any combustion appliance in a tight building must be either a sealed combustion unit that draws its combustion air directly from outside through a dedicated pipe, or the building must have a controlled fresh air supply. This is not optional. This is not a detail you figure out later. It is part of the design from day one, which leads directly to the ventilation question. A building this well-sealed has excellent thermal performance and a serious ventilation challenge. You cannot crack a window at -40. You will destroy your interior temperature in minutes, and you will introduce a massive amount of extremely dry, cold air that your heating system then has to condition. The solution is a heat recovery ventilator, an HRV. An HRV is a mechanical ventilation device that simultaneously exhausts stale interior air and pulls in fresh exterior air, but routes both streams through a heat exchanger before either reaches the living space. The outgoing warm air surrenders 60 to 80% of its heat to the incoming cold air, without the two streams ever mixing. The result is continuous fresh air, removal of moisture and carbon dioxide from the interior, and minimal heat loss from the ventilation process. In a passive, loosely built structure, ventilation happens accidentally through air leaks, draft around windows, gaps in framing, uninsulated penetrations. You lose heat constantly, and you have no control over it. In a tight, foam-insulated structure with an HRV, you have complete control. You choose how much fresh air comes in. You choose when, and you recover the vast majority of the heat that would otherwise be thrown away. This technology is standard practice in Scandinavian countries, in Canadian passive house construction, and increasingly in high-performance Alaskan builds. It is not exotic. A residential HRV unit appropriate for a small structure costs between $600 and $1,500. It is one of the highest return investments in an entire build. Let's talk about real numbers, because a video like this means nothing if a viewer cannot figure out whether it is actually possible for him. A Quonset hut kit in a size suitable for a cabin or permanent dwelling, roughly 20 feet wide by 40 feet long, giving you 800 square feet, typically runs between $8,000 and $20,000 depending on the manufacturer, gauge of steel, and configuration. That gets you the shell, the end walls, and the hardware. Spray foam applied professionally to that footprint at 4 to 6 inches thickness will run another $8,000 to $15,000, depending on your location in Alaska and how accessible your site is. This is the largest variable in the budget and the one most worth getting right. Foundation work, whether an insulated slab or an elevated wood frame, will run anywhere from $3,000 to $10,000, depending on ground conditions, site access, and whether you hire it out or do the labor yourself. A quality wood stove or propane heater, installed correctly with proper flue, combustion air, and clearances, runs $1,000 to $4,000. An HRV unit, insulated ductwork, and installation adds another $1,500 to $3,000. Doors, windows, electrical, and interior finishing are highly variable, but a no-frills functional interior can be done for $5,000 to $10,000. Total realistic range for a complete, functional, properly insulated Quonset hut dwelling in Alaska, $35,000 to $65,000. Compare that to a conventional stick frame cabin of equivalent size in Alaska, where material and labor costs routinely push past $150,000, and where the thermal performance is often dramatically worse. You are building something superior for less than half the price. For a hunting cabin, a remote workshop, a bug-out structure, a homestead, or a year-round off-grid dwelling, the economics are compelling, especially when you factor in durability. A properly built Quonset hut with foam insulation and a good foundation will stand for 50 years with minimal maintenance. The arch does not rot. The foam does not compress or settle the way fiberglass does. The steel does not burn. There is one more thing worth understanding about the man in this image, because it is the thing that actually makes the story. He is standing outside at -40 degrees, relaxed, pointing at his front door like a man showing you his living room, not shivering, not rushing inside, not looking stressed. That is the posture of a man who solved a problem completely. Most people who move to or build in remote Alaska spend their winters in a state of low-grade anxiety about heat. Is there enough firewood? Is the propane going to run out? Is there a gap somewhere that is leaking cold air? Is the pipes going to freeze if the stove goes out at 3 in the morning? That anxiety is not weakness. It is a rational response to living in a poorly built or marginally insulated structure in one of the coldest places on Earth. This man does not have that anxiety, because he built his structure correctly the first time. He used the right shape, the right insulation, the right foundation, the right heat source, and the right ventilation. He did not cut corners on the foam. He did not skip the floor insulation. He did not oversize the heater and pretend that brute force was a strategy. He built a system, and the system works. That is the real lesson here. Not just the Quonset hut, not just the spray foam. The lesson is that cold climate building reward systems thinking. Every component has to be designed to work with every other component. The shell sheds snow. The foam eliminates heat loss through the walls. The insulated floor eliminates heat loss through the ground. The small efficient heater runs the numbers that the foam makes possible. The HRV keeps the air clean without throwing away the heat. Pull one piece out, and the whole thing suffers. Put all the pieces in, and you get a building that laughs at -40 degrees. If you are a man thinking about building in Alaska or in any extreme cold climate, here is what to take from this. Stop thinking about heating as the solution to cold. Heating is the last mile. The building envelope is the solution. Get the envelope right, and the heating becomes almost an afterthought. Closed cell spray foam is worth every dollar. Do not cheap out on it. Do not substitute open cell foam to save money. Do not leave gaps thinking they are small enough not to matter. In extreme cold, small gaps are where your money bleeds out dollar by dollar, all winter, every winter. Do not neglect the floor. It is the least visible part of the thermal envelope, and the most commonly overlooked. It will cost you as much in heat loss as a compromised wall. Size your heater to your insulation, not to your fears. If the building is built correctly, a small heater is not a risk. It is a correct answer. Install an HRV, not as a luxury, as a component. It completes the system. And if you are choosing a structure type for extreme cold and you have not seriously considered the Quonset hut, consider it now. The arch is not a compromise. In this climate, for this application, it is genuinely one of the best structures a man can build. -40 outside, 70 inside, no grid, no massive fuel bill, no anxiety, just a man, a door, and a building that works. That is what good engineering looks like. And now you know exactly how it is done.